Hey, welcome back to Comp 1113, Unit number 4, Boolean Algebra, video number 2. Today we're going to be talking about truth tables. We'll do some proof of Boolean expressions using truth tables. Then we'll move on to some Boolean postulates and theorems. And then we'll use those theorems to do some Boolean algebra and some simplification. You might be wondering why you would learn Boolean algebra, and as we're going through this, it looks a little bit abstract, but this is something that a programmer would use every day whenever they're controlling an if statement or a while loop, or if they're doing anything with databases. They're using logic at all times. So understanding Boolean algebra will be a useful tool for us going forward. I have a little expression here where I have x or not x and y, and someone tells me it equals x or y. Now that's a nice simplification. It would be nice to take this complicated expression and be able to simplify it to the expression on the right side. And that's where we're headed with this. But for now, let's prove that it's true. And we can do that proof using a truth table. What we can do is build the truth table for the left side and build the truth table for the right side. And if the two truth tables are the same, well, then we've shown that this equation is valid. So I see in this equation that there are only two variables. So we have our x and we have our y, and we list all the permutations, and we list them in order. This is the binary number 0, the binary number 1, 2, and 3. So there are 4 permutations. Then we will build the truth table for this left side. To build that, we have to know our order of operations, which means we should do a not before we do, say, this or. So let's build a column with x not. Basically, we take everything that's in our x column and we just rewrite it using the opposites. Everything that was true is then false. Next, we'll take this column and we will AND it together with y. So we'll keep our eye on these two columns and we'll apply the AND operator because we know that we should do this AND before we do this OR. To do that, we have false and true is false, true and true is true, false and false is false, true and false is false. So we just use our rules for AND here to create this column. Now we want to take x and OR it with this column. So we'll be looking, our eye will be on this column and on the first column. So in the first row, we'll be applying OR to false or false should give us false. And in all the other spots, anytime you have any part of it that's true, it will be true. So I have false or true, which gives me true, or true or false is true, and true or false is also true. So we've built the truth table for the left side expression. Now all we have to do is build the truth table for the right side. And because it's built out of x and y, I'm just going to tack it onto the same table. I'm looking at my x column and my y column, and I'm applying the OR operation. False or false gives me false. False or true gives me true. True or false gives me true. True or true gives me true. Now, if we compare these two columns, we see that they are identical. So no matter what permutation of inputs you have, you get the same output. And because of that, this expression is true. It's an exhaustive proof. Not exhaustive because it's hard, it's exhaustive because we've exhausted all possibilities. We've shown it works for every case, and therefore it's true. This is a valid proof method. It becomes a bit tedious if you have 9 variables, however. With 2 variables, truth tables are great. 3 variables, they're okay. 4 variables, all right. But 5 variables, we're into 32-row truth tables, and it becomes a bit difficult to work with. So hopefully we can come up with a bunch of expressions that are true, and then we can apply them once we've proven that they are true. And then we don't have to always use truth tables. But truth tables will always work. And they aren't too much, they aren't too difficult to do. They do take a little bit of practice just so you don't make little mistakes. So the number of variables, I was just saying, affects how many different Boolean expressions you can have. An example, here's 3 Boolean variables. I've listed all the permutations. They're the numbers 0, 1, 2, 3, 4, 5, 6, and 7. So there are 8 possible inputs. How many different outputs could I have then? Here's one. They could all be 0. That's called a contradiction. When, regardless of what you input, the function outputs 0. There are many other options. I could have a 1 in this first spot and then zeros everywhere else. Or I could have a 0 in the first spot and a 1 and then a 0 everywhere else. I'm not going to be able to list them all because there's quite a few. Each one of these spots has 2 options. So I have 2 to the 8th power permutations, or 256 unique Boolean functions that I can make out of the variables x, y, and z. Now, there's an infinite number of expressions I can write down, but many of them will be equal to one another. Like our last example, we had 2 expressions, but they output the same truth table. So on 3 variables, there are 256 unique ones, even though I can write down an infinite number of expressions involving x, y, and z. Just combine them with lots of ands, ors, and nots, and you can come up with an infinite number of ways to write them. However, you'll only end up with 256 distinct truth tables. The general rule here is for n variables, there are 2 to the n permutations, and then 2 to the n different functions. So you can see it grows fast. Before we can fully build Boolean algebra, as a formal mathematical field of study, we need to start out with some basic given facts, which we've already established back when we were first talking about and, or, and not. Now we're just formalizing this, and these things are going to make a lot of sense. Something that's a postulate just means it's like a definition. We don't prove it. We just have defined these to be this way. And then we assume that that is true, and we build all our other rules from there. An example of that is if something is x, x is 1 if it isn't a 0. In Boolean algebra, everything's a 0 or a 1, so no kidding. If it's a 0, it's not a 1. So I don't even know if we would ever need to write that fact down, but it is a fact. The and rule, false and false equals false. True and true equals true. True and false equals false. Like we learned these when we learned what and meant. And here are the corresponding or versions. This one is particularly weird, true or true equals true. When you write that down and show that to your friends, That might cause some alarm. And then the next one is the not rules, which we've also talked about. If you're not a 1, you're a 0. If you're not a 0, you're a 1. So those are the basic definitions that we start with. Then we can start building the basic laws and theorems that allow us to manipulate Boolean expressions. Before we do that, some of you might already be familiar with some of this stuff if you've done some set theory. There's a perfect link between Boolean logic and set theory. In set theory, we often use these things called Venn diagrams, and we have the whole universe being, say, this box, and then we let X be represented by a circle, the area of that circle. So if I want to represent not X, it's everything not in the circle, and I can shade that. If I wanted to know what X was, I would shade X. To do the or and the and, I guess I would need another circle. So I'll have to include another circle there for Y. For or, we said it's anything in X or anything in Y or anything in both. That's called the union of X and Y. So X union Y. And for and, that's the stuff that's common to both X and Y. So it's this football shape in the middle here. And we'll use an intersection symbol for that if we're talking about sets. But the rules are the same for both. What you can do for logic, you can do in sets. And maybe you're more familiar with this notation. I kind of like showing the parallel to the set theory so that we can sort of visualize some of these things rather than have everything just be equations. In Boolean algebra, we have the commutative property, which we're pretty familiar with from regular algebra. X and Y is the same as Y and X. So the order doesn't matter when you're anding, and the order doesn't matter when you're oring. So that's to be expected, I would say. The associative property from regular algebra applies to Boolean algebra as well. It doesn't matter how you group things. If everything is linked by and, it doesn't matter if you and the first two and then and with the next one, or and the second two and then and it with the first. Same with ors. So this stuff should be very familiar to us from algebra, or even just arithmetic. The distributive property exists in Boolean algebra. You can take a variable on the outside of brackets, and if it's anded with things inside the bracket, you can just distribute it in. You've probably, imagine doing this as foiling from regular algebra. With this equation, note that you could be starting on the right side of the equation and go to the left side. So basically, this is your distribution and your factoring. So factoring is allowed in Boolean algebra. We could probably establish that this works. We could maybe do it by visualizing it. I translated this expression from Boolean logic into sets. So now I have set Z, set X, and set Y. And I translated my ands into intersections and my ors into unions. I could draw the picture for the left side of the equation and draw the picture for the right side of the equation. And if they match, that's pretty strong evidence that this is true. It's actually not a proof. It's more of a way to visualize it, but I wouldn't try to prove something that way. If we wanted to prove this, I think it would be best if we used a truth table. However, I'm not going to do that. I'll leave that as an exercise for you. Build the truth table for the left side, build the truth table for the right side, and show they're the same. I thought I'd draw it with 3 variables just to show us a Venn diagram with 3 sets. To construct this, I have X or Y, or X union Y. That means I'm going to shade anything in the X region and anything in the Y region. And if it overlaps, that's fine. So here we go. I don't want to step too far. So we now have X union Y. Next, we want to intersect that with Z. So where does the red region here intersect my Z bubble? And that'll just be right here. As you can see, my cursor sort of moving around. That's where we intersect or overlap with Z. So we'll ultimately just end up shading this. So this is our Venn diagram for the left side of the equation. Now we can go over to the right side and see if it matches. We'll have to be careful on this side. We're assuming order of operations here, so we have to make sure that we do our intersections before our unions. So let's do Z and X. That's where Z intersects with X. So that's this football region that I'm highlighting right here. Then we should construct Z and Y. That's this football region. And then we OR those two together. So we have a region here, and we have a region here, and they get ORed together, meaning anything in either of them gets counted. So let's see it draw here. Put them together, and ta-da. They match. So I feel pretty good that this is a true statement. If you're not sure yet, definitely make the truth table and convince yourself that this law works. Because once you've proven it, once you know that this is true all the time, you can then just use it. You don't have to be reinventing the wheel each time. Here's a property that we don't have in regular algebra. I said Boolean algebra has one more property. I shouldn't have said that. This should probably read just Boolean algebra has a property that is not familiar, because there might be other ones. But this is one that is not familiar about the distributive property. It's really neat when you have Z or and then two variables that are ANDed together, you can distribute the Z into the brackets, but it takes this OR with it. In the typical distributive property, we have an AND here and an OR here. But now we can swap them around and it still works out. Basically, we can turn it from the sum of ANDs into the AND of sums. And again, remember that these properties work in both directions. So if you have an expression that looks like the right side, you could factor the Z plus out and get the left side. Again, we could prove this. I don't know, it's not really proof. We could try to visualize this using Venn diagrams. On the left side here, we could first construct the AND. X and Y is this football. And then we have to OR that together with Z. So it's this football combined with anything that's in Z. And there's our region. That's the shaded region for the left side. Now we can go and build the right side and see if they match. Now we have brackets, so it's clear that we should do these ORs first. We have Z or X. So that's this group with this group. Like that. And now we'll build this other OR, which is Z with Y, which will be these two circles. And now we put those two together with an AND. So we visualize this group and the previous group and we try to imagine where they overlap, because that's what intersection means. And sure enough, we get a match here. The two groups are the same. If you don't buy this Venn diagram argument, which you might not, you could certainly make the truth table for both sides. It's not bad to make. In fact, it probably would have been faster because there are only 3 variables. There aren't even any knots in it. All you have are ands and ors. It would build very quickly. The reason I don't like to consider this a proof is we've shown that the 2 pictures look the same when we draw them in this certain way, where we put x here, y here, and z here. But is it always true? Maybe I could put the whole y bubble inside the x bubble and have the z bubble separate. We'd have to repeat the whole thing all over again and show it works for that picture too. So this isn't showing that it works for all such pictures, which is why I prefer the truth table, because that does show it works for every possibility. We have some other theorems. Many of them are kind of obvious. The universal bound theorem, where if you AND with false, you get false. Anything ANDed with false is false. And then the OR version is anything ORed with true is true. Again, here's a statement that is not true in regular arithmetic. Identity theorems. Here's an AND identity. When you AND with 1, you don't change anything. It just has a fancy name, identity. There's an OR identity as well. When you OR with 0, you don't change it. So just like in regular arithmetic, you have the multiplicative and additive identities. Now we have Boolean versions of those theorems. These two are exactly the same as their multiplication and addition theorems. Up here, the universal bound ones are, at least theorem 9b is new to us. I started giving these theorems numbers and codes here just so that we don't have to say their names all the time. Whenever we use one of these theorems, we can just mention its code rather than its name. Of course, these codes are made up by me for this course. So if you're talking to a student at SFU saying, I learned theorem 9b today, they won't know what you're talking about. But if you said, I learned the universal bound theorem for addition, that's what theorem 9b is. But that's a mouthful. So I think using the codes, I'll give you a formula sheet, essentially, with all of these on it. And then when we're using them, you can just mention the code rather than, identity for addition for theorem 10b. And the cheat sheet will be set up in such a way that anything that's an A theorem is an AND type theorem, and the B theorems will be all OR type theorems. So there's a bit of method to the madness. Technically, we should be proving these things. We should make a truth table for this one, and make a truth table for this one, and this one, and this one. But I think they're pretty obvious. If you just reason through them, you'll believe them. But if you're not sure, or if you don't believe them, you should make a truth table for them. Idempotency theorems, that's a mouthful. We have the AND version. Something and itself is just itself, which is not true in regular algebra. That would be x squared. But in Boolean, imagine if you have 0 and 0, you get 0. 1 and 1 is 1. So no matter what I put in here, it always will yield the same thing. For OR, 1 plus 1 is 1, and 0 plus 0 is 0. Therefore, this theorem must be true. So I sort of just talked my way through the proof in the truth table. Because there's only one variable. X here is a 0. Make sure it works for 0. x could be a 1. Make sure it works for 1. The negation theorems, we have something and its opposite is always false. Imagine they're always opposites. So if x is 1, then y is 0. And anything ANDed with 0 is 0. Or the other way around, x is 0, x naught is 1. Well, 0 and 1 is 0. And the addition version, something plus, I shouldn't say plus, something or its opposite has to always be true. The not operator has a fun little property called double negation. If I double not something, if I not and then not again, I get back to where I started. There I only needed one theorem. There wasn't an and an or version. The absorption theorems are awesome, but not that intuitive perhaps. Here's a theorem, theorem 14a, where we have a relatively complicated expression, and it simplifies to just x. We could draw a quick Venn diagram, make the left side of this equation, construct x and y, and OR it with x. So here's x and y, and then all of x. We put them together with OR, and we get x. So it's pretty slick. Nice for simplification. Now, why would we ever want to simplify? Well, to make things run more efficiently. As an example, if you have an if statement in your program, when you were thinking about it, you thought, if this is true and that is not true, or this is true and this is not true, and this or that is true, then do something. If you can simplify that complicated expression, you can make the code run more efficiently. Now, what was natural for you to think of might have been the complicated version, because you were sort of thinking about all the different cases that can occur. But after coming up with that and testing to see if it works, you can then simplify it to its optimal form and improve the efficiency so you don't have to evaluate as many operations. Here's a quick example. We can prove this thing using a truth table, and it would be really fast because it's only two variables. Or why don't we try another technique where we use the theorems that we now know and love and believe. So let's use our previous 13 theorems to prove theorem 14. This is often how higher math works. We start with a bunch of smaller theorems and then we build new ones from there. I'm going to take the left side of this equation and try to prove it equals the right side. So I'm going to apply theorems to the left side, the more complicated side. To do that, I looked at the left side and I noticed that there's an x in both terms. So I decided to add a 1 onto the first term. You'll see why in a second. Anything and 1 is just itself. That was theorem 10a. So I took this x and wrote it as x and 1. And the reason I did that was now I can look at this expression and see that I have an x in the first term and an x in the second term, and we can do the factoring. So that's the distributive law. We can take the x and out of each term, and we're left with a true or y. Now we look at this expression and see what we can do. Does this 1 or y look familiar? Sure it does. We have a theorem that says true or anything equals true. It's theorem 9b, the universal bound law. Now we can take this expression and again apply theorem 10a, which said anything and 1 is itself. So we're to x. So we took the left side of the equation and we applied a bunch of rules until we got to the right side of the equation. That is a proof of this expression because all of the rules that we used along the way are known to be true. So we're going to do a bunch of those. I call it proof, but I mean, this is, somebody asked one day if, well, are we doing proofs in this course? And I guess this is a form of proof, but it's more of a, I consider this more of a show something is true rather than something as formal as proof. But it's a good gateway into more formal proofs. So it's okay to use that terminology, I suppose. Here's a Boolean expression, a rather complicated one. It suddenly went from really easy to quite difficult. And it has that everyone's dreaded word here, simplify. We don't even know what it equals. Our goal is to apply Boolean theorems to this and hope that we can make it look nicer. That may not be the case. Maybe this is already the best it can look. But all we can do now is try a bunch of those theorems. And it's difficult at the beginning because you don't know them. But as you do more of these problems, you get familiar with what you can and can't do. But each time you do something, you have to justify it. So anytime we use one of our theorems, I want to write it down. I'm looking at this expression, and then I look back at our, known theorems. We had the distributive law. And I'm noticing that it looks familiar here. I notice that there's a Z0 in these two groups, which kind of looks like this form, where we have an X in both of those groups. So basically, I'm going to rewrite those in order. So the first one, I didn't change at all. But the second one, I just put in the right order. I just swapped these two around. And that way I can see it lines up here. X lines up with Z0. My X is essentially Z0. My Y is this thing, U0 ANDed with Z. So I can express these two variables with one variable. And this Z here will represent X with Y0. You see that these two pieces aren't equal to each other, so I need to use a different letter for each. But now I can apply the pattern. My Z0 is an X. My U0 Z is a Y. And my XY0 is Z. I tried to color code this a little bit so you could see how this works. I'm just using the format. It's like a template. Now my Y is equivalent to this piece. So I'm going to write that over here. And then I'll put my Z over there as well. And don't forget about this little trailing piece that we didn't touch yet. So basically we took the stuff in brackets and we simplified that to this. Now we look at our new expression and we have options. Maybe you're looking at this and you see that there's a Y0 here and a Y0 here, and you'd like to factor that. Certainly that's an option. I went a different way just to prove that I could. I know theorem 14D. It's another absorption theorem. It works like this. If you have something plus its opposite ANDed with something else, it equals the something or the something else. Say that 10 times fast. I notice that I have a Z0 here and a Z here. That's very similar to this pattern. I have something or its opposite. I have something or its opposite. You notice that's really weird that this one has a knot and this one doesn't, but the pattern is just that the two things are opposites one another. So basically my X is Z0. And then this u naught x y naught will be my y piece. I don't know why this came flying in here, as we're not currently doing this right now. But yeah, be careful of your knots, I guess. When you have knots outside of groups, we'll have to learn how it applies within the group. I guess I put that in there so I wouldn't forget to mention it. So yeah, my y piece of this is u naught x y naught. And now I'm just going to take this expression and rewrite it like this form, x plus y. So it'll be z naught plus u naught x y naught. And then don't forget the other piece that's tailing along. And then finally, you'll notice that these two have y naughts in them. You wanted to do that probably at a previous step, maybe factor them out, or we can apply another absorption theorem. You might not have thought to do this, where you have something or the same something ANDed with something else. Something or same something ANDed with something else is just the something. So all this mess right here is going to just collapse and become y naught. And we get our answer. I think it will not get any simpler than this. This ugly expression that we started with simplifies down to z naught or y naught. If you don't believe me, make the truth table for this expression up here, and then make the truth table for this expression here, and you'll see that they're the same, assuming we didn't make any mistakes. There's more than one way to get through this Boolean proof or Boolean simplification. You just sort of feel your way through. Sometimes it will be hard to tell when you're done. And we will cover that a little bit later as to how do you get these things into their optimal form. But for now, just feel around, mess around with them to get it as simple as you can. In the previous slide, we had something called I had a tripping hazard that I wanted to make sure we didn't commit. That was basically De Morgan's theorem. It's theorem 15. We've done theorem 14 was absorption. Now theorem 15 is De Morgan. It helps us deal with the knots. If you have a knot outside of brackets where you have things that are ANDed together, it's weird. You don't just move the knot into the brackets, you also change the operator. So if you have two variables that are ANDed together, when you distribute or move that knot into the brackets, it changes the operator. We could draw the Venn diagram for these. Here's x and y, and then we'll negate it. And then we can build the other side of the equation, which is not x combined with not y. And we put those two pieces together with or, and we get the same picture. That's theorem 15a. There is a theorem 15b with an or. So it would be x or y negated. Sneak it in there. Which is x naught and y naught. Again, a truth table is probably a better way to prove these. We'll call this one theorem 15b. And it extends to more than two variables. If you have x, y, z naught, it just becomes their sum. X naught, y naught plus z naught. Same with the and. You can do multiple terms. Here's a relatively simple looking expression. Thought maybe we'd try to do this one the old-fashioned way. I think what I'll do is I'll skip on over to OneNote for solving that. And I'll also open up a list of all the theorems. It's nice to see them all in one place. So far, we've been just sort of attacking these things kind of line by line. Now you can see them all together. We'll leave this open for our reference as we try to simplify this expression. When you're simplifying these things, it's hard to know where to start, especially when you're first learning this. I say, just try something. If you have to cross it out or erase it, no sweat. I'm looking at this expression and I notice that there's an A and an A naught here. Maybe I can do something with that. With the second and third terms, I see they both have a C naught. Maybe I can do something with that. That's encouraging. Or maybe I like to look at the first term and the last term and see that they both have B naught. I really liked seeing that C naught being in both of these two. So I'm tempted to try the factoring. Now I have to go and find what law let me do that. So I look over at my cheat sheet and it looks like this is what we did. That's L8A, the distributive property of multiplication over addition. Now, you get to this point and you just throw your hands up in the air and go, well, I don't see much else I can do. I'm stuck. Maybe that's it. Maybe it was already in its simplest form. Or maybe you get desperate. Maybe you try some of the other versions. Ah, that didn't work. So maybe if I go maybe if I factor the B naught out. Remember the first term had a B naught, and so did the last term. Like that. Like I did this term with that term and factored. But I still feel like I'm stuck. So I'm going to show you a trick. This is a trick that you probably wouldn't think to do until you've seen the trick. I notice that the first term doesn't have any C's in it, but these two both have C naught. Then I look at the second term and I notice it doesn't have any B's in it, and the other two terms have B naughts. Then I look at the last term and I notice it doesn't have any A's in it, but these two have A's, but they're alternates, they're opposites of one another, and that's what I'm looking for. Check this out. I'm just going to throw an extra 1 in here because I can. Anything and 1 is itself. So I can always just and with 1. That's theorem 10a. I'm going to write that down as my reason for this step. Now here's where the real magic comes in. I'm making this expression worse in order to make it better. I'm going to write the number 1 in terms of some variables. I go and look at my cheat sheet over here, and I see that 1 equals x or 1. That's one option. But here's a better one. 1 equals x or x naught. So I could write x or x naught here by theorem 12b. But why the heck would I want to get x's into this thing? I don't want to introduce a new variable. So I want to use one of my existing letters. So I could use a or a naught, b or b naught, c or c naught. But I'm going to use a or a naught. The reason being is that this term has an a in it and this term has an a naught in it. So there's a method to my madness here. I'm introducing an A and A naught because I already have some of those. Now distribute. That's L8A. Right? We're taking an expression like this and we're doing distribution. Now, fun stuff happens. You see that there's an AB naught in this one and an AB naught in that one. When that's true, we can factor. So we can factor AB naught out. And we're left with a 1 for this piece. I technically maybe should have added a 1 on first. But I think you're used to this enough from regular algebra that I think we can get away with sort of skipping that step. And now look at the other two terms. I have A naught, C naught, and over here I have A naught, C naught. So I can factor that out of those two. And I'm left with 1 or B naught. Again, it's just L8A. Whenever you're factoring, you're using L8. Now we can simplify those. I need a rule for true or anything. So I go over to my cheat sheet, and the first column is all and stuff. So I know I need to start looking at my or stuff. Aha, true or anything is just true. That's theorem 9b. And I can do that twice here. And now, how do I get rid of these ones? It's an and problem. So I'm looking in the and column. I find, I find x and 1 equals x. So those ones are just gone. By theorem 10a. AB naught plus A naught C naught plus B naught C naught equals AB naught or A naught C naught. I don't think I can get it any simpler. In fact, at first I thought it already was as simple as it could be, but we did manage to squeeze a little bit out of that thing and make it quite a bit simpler. Like we removed an or and an and a couple of nots. So this expression is more efficient. I think this is a sort of a fun thing to learn how to do. You get used to applying these rules. Most of the rules you do sort of know. You know, most of the stuff that you do is what you can do in regular algebra. And then what I like to do is keep my eye on the absorption theorems so that I can be more efficient. In fact, we could have solved this in fewer steps. If I look back at this thing, when we were at this stage here, we have AB naught or AB naught C naught. Well, if you have x or xy, that equals x by theorem 14a. So if you have something like AB naught plus AB naught C, that just equals AB naught. Like you can think of the AB naught as x. It takes a while to get used to seeing, you know, that a group of variables can equal a single variable. But that's legal because it's all just zeros and ones. So we could have done this a faster way without ever having to factor if we knew these absorption theorems. And the absorption theorems are the ones that we probably are least familiar with. So as you're working through problems where you're asked to simplify using the theorems, I would keep my list of theorems open, maybe print this out, stick it on your wall somewhere so you can constantly be absorbing it. And then whenever you're doing a problem, keep your eye on this absorption theorem because it will often simplify questions really fast. We'll do some examples when we do, things in lab. I think that's enough for this unit today. We'll do some more of this as, in our exercises, and we'll move on to some more Boolean ideas in the next section. Hope you all have a good one, and I will see you next time.